To generate and to amplify radio waves with very high frequencies, so-called microwaves, special tubes are required. For example, the klystron. Consider a simple klystron amplifier. The essentials of this simple klystron are the electron beam, and two metal boxes known as cavity resonators. The cavity resonators have a potential which is positive with respect to the cathode. Thus, the electrons emitted by the cathode are accelerated towards the first resonator. Because the resonators have apertures in the form of grids, the electrons will continue until they reach the collector, which is at the same potential as the resonators. Therefore, in the region between the first resonator and the collector, the electrons would have a constant speed if it were not for the influence of the cavity resonators. In reality, the first cavity resonator is supplied with the weak high-frequency signal which is to be amplified. This signal will initiate an electromagnetic field inside the cavity. Due to this field, the velocities of the electrons passing through the first resonator are modulated. On arriving at the second resonator, the electrons will induce there another electromagnetic field of the same frequency. This field is so strong that it is possible to extract a large signal from the second cavity. To understand this amplification process, it is necessary to study the behavior of a cavity resonator in detail. There is a certain similarity between a cavity resonator and a conventional resonant circuit. A simple resonant circuit consists of a capacitor and an inductive loop. It is known that a conductor contains free electrons. Charging the capacitor to obtain a voltage of this polarity means that many electrons are removed from the upper plate and an equal number of electrons are introduced into the lower plate. Thus, there are two charged layers. One layer has an excess of electrons and is therefore negatively charged. The other layer has a shortage of electrons, which reveals itself as a positive charge. The electric field lines are directed away from the positive charge. If the capacitor is charged with the reverse polarity, the direction of the field lines is also reversed. The displacement of electrons in the loop constitutes an alternating electron current, which is symbolized by the variations of the green arrow. The alternating current gives rise to an alternating magnetic field. The magnetic field of the loop is out of phase with the electric field of the capacitor. At the moment that the magnetic field is at maximum strength, the electric field is zero. A quarter of a cycle later, when the electric field is at maximum strength, the magnetic field is zero. There are two similar situations in one cycle at which the fields have the reverse direction. Thus, the oscillation which was started by loading the capacitor represents a certain amount of energy that is continuously exchanged between the electric field and the magnetic field. The smaller the value of the capacitor and the inductivity of the loop, the higher the frequency of the oscillation, or the resonant frequency. With this simple circuit, a rather high frequency can be obtained, because the inductance of a single loop is very small. To obtain higher frequencies still, the inductance can be further reduced by placing two or more loops in parallel. This results finally in the formation of a closed resonator having certain very high resonant frequencies, which are determined by the dimensions and shape of the cavity. In a closed resonator, the magnetic field, as well as the electric field, is confined to the interior of the cavity. The associated currents and charges are to be found in a thin layer of the interior surface of the resonator. The first resonator of the klystron is excited by the external signal which is to be amplified. This signal, often introduced via a coaxial cable, must have a frequency at which the cavity can resonate. The current in the coaxial cable sets up a magnetic field, which in turn brings the resonator into operation. That is to say, that also an electric field is originated. It is sufficient to consider only the electric field in order to understand the modulation of the electron beam entering this first cavity resonator. The electric field lines indicate the direction of the force acting on a positive charge. The electrons, being negatively charged particles, will therefore be accelerated if they move against the direction of the electric field. On the other hand, the electrons will be decelerated if they move in the same direction as the electric field. With the alternating electric field present, the electrons will thus be alternately accelerated and decelerated. Consequently, they will enter the field-free space between the two resonators at varying speeds. In this space, known as the drift space, the fast electrons will overtake the slow ones and bunches will be formed. The second resonator is located in the position where the bunches contain the greatest number of electrons. The bunches arrive at the second resonator at intervals corresponding to the frequency with which the first resonator oscillates. As both cavities are made identical, these intervals also correspond to a resonant frequency of the second cavity. Therefore, the latter starts to oscillate. The alternating magnetic field inside the second cavity is partly linked with the coaxial cable and thus initiates the output signal. Summing up the whole action of the klystron. The electrons coming from the cathode enter the first resonator with high kinetic energy. This first resonator is set into oscillation by the input signal so that the beam is modulated and bunches are formed in the drift space. These bunches, in turn, set up an electromagnetic field of the same frequency in the second resonator. From this field we can extract a larger output signal. We must now consider why the output signal is larger than the input signal. A constant stream of electrons enters the first resonator so that almost equal numbers will be accelerated and decelerated. Thus, the average kinetic energy of the outgoing electrons is nearly equal to the energy of the incoming electrons, and almost no energy is taken from the field of the cavity. At the second resonator, however, the majority of the electrons are in bunches, and these are decelerated. Only very few electrons are accelerated. The result is that almost all the kinetic energy is converted into electromagnetic energy. The electromagnetic energy of the field which produces the output signals. Amplification of such a two-cavity klystron is too low, then multi-cavity klystrons may be used. With a very small signal applied to the first cavity, the bunches arriving at the second cavity are very weak. But they will set up a field there which is strong enough to produce more concentrated bunches at the third cavity, and so on, enabling very large amplification factors to be obtained.